Hi, everyone. Let's get right to it. If you take David's coin, you flip it 100 times, and you get 59 heads in 100 flips, is that unusual? I wish I could give you just one response, but actually, it depends on the analysis. It's more complicated than you might think. And we're going to use 4 methods to analyze this question. Is 59 heads on 100 flips of a presumably fair coin unusual? Or is that too unusual for the assumption of a fair coin to hold up? Remember, our null hypothesis is that the coin is fair. Or P, the probability of heads, is 0.5. The coin is fair. P, the probability of heads, is 0.5. In example 3, a magician's coin was flipped 100 times, and we observed 59 heads. The null hypothesis states that the coin is fair. Let's say that's David's claim. My coin is fair. The alternative hypothesis, H sub 1, states that the coin is not fair. These are complements. Use the significance level alpha equals 0.05, which is standard, but not always the case. So make sure you check on the value of alpha in the problem. Again, a hypothesis test has 3 key ingredients: a null hypothesis, an alternative hypothesis, and a value for alpha. Alpha you're basically given. The null and the alternative may depend on the way that the question is phrased. But for right now, it's fairly straightforward. The null says the coin is fair. We can base calculations on that. The alternative says that the coin is not fair. Do we decide to reject or not reject the null? Well, that's going to depend on if we use a one-tailed or a two-tailed analysis. It depends on what our value for alpha is, although I am telling you what value for alpha we're going to take. Different analyses will lead to different decisions, actually. And what do we conclude about the assumption that the coin is fair? What do we do with the null hypothesis? That assumption. We'll use 4 methods to answer these questions. Different methods lead to different decisions and different conclusions. Even for the same value of alpha, that could potentially happen. Method 1. For example, you could have a difference between your conclusions from a one-tailed analysis versus your conclusions from a two-tailed analysis. Method 1, let's use a one-tailed p-value. All right, so basically, what's the probability of getting at least 59 heads by chance? If you use, say, a normal approximation with a continuity correction, that's why you see 58.5 over here, then you find that this right tail probability is 0.0443, or 4.43%. In fact, if you go to my Excel worksheet, that confirms this. So the one-tail p-value, the probability that X is at least 59 heads, because remember, if you get 59 heads, then it's not fair to just look at p of 59. You should look at the whole tail, all right? Look at the whole tail. Add up all the probabilities from p of 59 through p of 100, which corresponds roughly to this area in here. Actually, the area of this is pretty close to the actual probability here, the sum of these probabilities. The area of this tail is actually a very good approximation. It is about 0.0443. Excel verifies that when it looked at the straight binomial distribution. Again, the one-tail p-value is about 4.43%. But now wait, is this too low? When do we reject the null? We're going to make a decision. Do we reject the null or not? Our decision. Do we reject the null or not? Well, the question we have to ask is this p-value low? Is this p-value low? What does low mean? Is it less than alpha? What was alpha? I'm saying in this problem, alpha is 5%, 0.05. So compare this p-value, about 4.43%, to alpha. So here's the p-value. And here is alpha. Compare the p-value to alpha. Is the p-value less than alpha or greater than alpha? Remember, I'm not going to have it be equal to alpha. Is the p-value less than alpha or greater than alpha? About 4.5%, that's less than 5%. That's less than alpha. So by this standard, the p-value is low. It's lower than alpha. The p-value is low. If the p-value is low, what happens to the null? The null must go, as in go away. We reject the null. We reject the null because the p-value is low. It's lower than alpha by the 5% standard for alpha. We reject the null. That is, we reject the assumption that the coin is fair. So if I get 59 heads and 100 flips of David's coin, and David claimed, hey, my coin is fair, that's the null hypothesis, we're going to reject that assumption. We're going to call David a liar, basically, or he doesn't know. What about a two-tailed p-value? So 59 heads, is that unusual? Well, what does it mean to be at least as unusual as 59 heads? In method 1, we said that at least as unusual meant getting at least 59 heads. Now in method 2, we're saying that at least as unusual, here, at least as unusual as 59 heads. Okay, here in method 2, that's going to mean getting at least 59 heads or at least 59 tails when you flip this fair coin, presumably fair coin, 100 times. It's a two-tailed analysis. By symmetry, remember we're assuming a fair coin under the null. By symmetry, this left tail probability, getting at least 59 tails, okay, that's equivalent to saying getting at most 41 heads. Again, I have continuity corrections here. Well, we just double this right tail probability we got earlier. When you double 0.0443, okay, the probability of getting at least 59 heads or at most 41 heads, right? That's about 8.86%. Now, is that low? Is it too low for the null to hold up? Well, we're asking the question, is it lower than what? Is this p-value lower than alpha? What was alpha? It was 5%. Well, is 8.86% greater than 5% or less than 5%? It is greater than 5%. The p-value here, I know I say it right here, but the p-value here is greater than alpha. The p-value, 0.0886, is greater than our pre-specified value for alpha. So the p-value is not low. By this standard, the p-value is not low. Before, in the one-tailed analysis, we said the p-value was low, and we rejected the null. Here, the p-value is not low. We do not reject the null. And by the way, not low does not necessarily mean high. I mean, 8 to 9%, we're saying that's not low, but it doesn't mean that that's high either, right? For example, speaking of the dating scene, not ugly does not mean beautiful. So if you're being told that a friend of a friend is not ugly, you're not going to assume that you're going to get someone beautiful. Brad Pitt or Angelina Jolie. All right. So the p-value is not low. We do not reject the null. So we do not reject the assumption that the coin is fair. So if David says, hey, my coin is fair, you get 59 heads and 100 flips based on a two-tailed analysis. Based on a two-tailed analysis. Well, we have some evidence against what David is saying, but it's not strong enough. The p-value is not low enough. The p-value is not low enough. See, remember, a lower p-value means stronger evidence against the null. Lower p-value means stronger evidence against the null. I realize that's a bit confusing, which is why the null might be better. If the p-value is low, the null must go away. Here, the p-value is not low enough. We do not reject the null. We do not reject the assumption the coin is fair. We do not call David a liar. That might be a bad idea anyway, because he might turn us into a rabbit or something, if he's really a magician. All right, anyway. Method 3, using a confidence interval. Remember, the null still states that the coin is fair, meaning the probability of heads, P, is 0.5 on the dot. I know that's not realistic, but according to the null, the coin is fair, P is 0.5 on the dot. The given value for alpha is 0.05. Please make sure not to confuse these numbers, right? Because you see a bunch of zeros and fives. Please make sure not to confuse these numbers. Alpha is 0.05, or 5%. So what kind of confidence interval do we want to look at? If alpha is 0.05, then 1 minus alpha is 0.95. If alpha is 5%, the complement is 95%. So we want a 95% confidence interval, or CI, for P, the probability the coin comes up heads. I had it up there, but I'll retype this. P is the probability that this coin comes up heads. For a fair coin, P is 0.5. That's what the null is saying. 0.5 is the hypothesized value for P under the null. I've never typed that. Let's do that. 0.5 is the hypothesized value for P under the null. Right. So using methods from before, or maybe you're using Excel, a 95% confidence interval for P is given by this, from 0.494 to 0.686. Now, according to the null, P is exactly 0.5. Is 0.5 in this confidence interval? The answer is yes. 0.500 is contained in this confidence interval. It contains the value for P hypothesized under the null, so we do not reject the null. So what's a way of thinking of this? I don't know. If the CI is away from this 0.5, if the CI is away, the null goes away too. I don't know. If the CI is away, the null goes away too. Right? If the CI is away from 0.5, here the CI is not away from 0.5. The 0.5 is contained in the confidence interval, so the null does not go away. We do not reject the null. Okay, it's like one of these safe guys in green. That might be a way of looking at it. Green means safe. So on this applet, right, there's a 95% chance, if this is the true value for P, there's a 95% chance that the CI is good, contains the 0.5, green, right? If the 0.5 is contained in the CI, if you get one of these green confidence intervals, okay, green light for the null, we do not reject the null. We do not reject the assumption the coin is fair. So if David says the coin is fair, we're not ready to call him a liar. And by the way, this corresponds to the two-tailed analysis from above. So in fact, as far as the underlying theory goes, the two-tailed analysis from method 2 and this confidence interval method from method 3, which is, in our class, a two-tailed method, right? We have a tail to the left here, a tail to the right here. We get the same decisions and the same conclusions from method 2 and method 3. As for method 1, the one-tailed approach, maybe there could be a same decision and conclusion, but maybe not. Method 1 could give you a different decision and a different conclusion. But methods 2 and 3 are equivalent in the sense that you'll get the same decision and same conclusion from either method. Of course, for the same value of alpha and the same sample data. Method 4, this will take you way back, the 2SD rule for unusual z-scores. Remember, your sample data is unusual if it's more than 2 standard deviations out. It's not so unusual if it's within 2 standard deviations of the mean. All right. Again, from lesson 10, the 2SD rule for unusual z-scores. Z-scores that are either less than -2 or greater than 2, so you're too far away from the 0, the center, they're considered unusual, and the corresponding x values are also considered unusual. Okay, so on this number line for z now, on this number line for z, here's -2, here's +2. If you're outside, if your z-score is too extreme, if your z-score is too extreme, then we're going to say that that's too unusual for the null to hold up. All right. If you're in between here, not so unusual. All right. So from before, we found that the mean was 50 heads. If you have 100 flips of a fair coin, right? 100 flips of a fair coin, all right? Then the number of heads is approximately normal, where the mean is 50 heads. The standard deviation is 5 heads. For 58.5, that's after continuity correction. Don't worry, you won't have to freak out about continuity corrections on your last homework assignment. But the z-score for that is going to be 1.70, which is not an unusual z-score, right? 1.7 is safely in here, right? It's not an unusual z-score, so we do not reject the null. So we do not reject the assumption that the coin is fair. Now, here's the thing. If alpha is 5%, then method 4 will usually be equivalent to method 2 and method 3, but there's a bit of discrepancy there. Okay. So we have some of these methods that tell us that the null should be rejected. We have other methods that say the null should not be rejected. This is what drives pure mathematicians bonkers about statistics sometimes. We have 4 legitimate methods that yield potentially different decisions and conclusions. I'll tell you one thing that is not fair, though. I didn't even list this. It's the first method that a student would come up with. What's the probability of getting exactly 59 heads? But that's not fair to 59 heads, because even the probability of 50 heads is not even 8%. It's not that high. So the most obvious method, I don't recommend. It's not fair to 59 heads. Okay, in later lessons, we're going to formalize hypothesis testing and also how we're going to write that final conclusion. What can we say to the layperson? And we're also going to talk about the traditional approach to hypothesis testing afterwards.